Boom. We're talking about friction. Friction Friday today. Who here skis or snowboards? Good. Should be a good year this year, I hope. Why do you not, when you get on your skis and you just go down the hill and you turn, why do you not just keep down the hill?
Friction.
Because of friction, yeah. So when you turn on your edges, you get that force of friction and it allows you to turn, right? What is friction anyways? Force of resistance. That's a good way to say it, Lizzie. Sean? It's something stopping you. Yeah, it always works against motion, yes? It's a strange force that way. Always. Always. Well, I won't get into it. Go like this. Fingertips on your table. You just push them across gently. What do you feel?
Heat.
Yeah, the table. Is it smooth?
It's smooth, but it kind of like stops. It's like this little like jaggy.
There is a force against your motion, yes? Can you feel, the table looks like it's perfectly smooth, but is it perfectly smooth? Does it have little ups and downs and things? Yeah, it does. That is what causes friction. If I put a ramp here, I have a ramp here, I might as well show you. And I roll this cart up the ramp. If this were perfectly smooth, and I rolled this along, it would just keep on moving, right? But if I have a ramp, now I must exert quite a good force to push this up the ramp, yes?
Yes.
What am I pushing against? Which direction does gravity pull?
Down.
Straight down, right?
Yes.
So why do I have to exert a force if I'm not pushing this straight up? Partly I'm pushing against friction, yeah, but we're going to see that. There is a normal force involved, yeah. You're sitting on a flat surface, so which direction is your normal force? Straight up, right? Gravity straight down, normal force straight up. Which direction is the normal force on this car? Yeah, Jake and Alexander are saying this, and that's true. Because it's perpendicular to the surface. So the ramp can't push against the car straight up, it pushes this way. And so when you pull the car up the ramp, you're not pushing directly against gravity because the normal force is working against part of gravity. The ramp is keeping the car from going straight down. But you have to work against some of gravity. And the lower it is, the less gravity you have to work against, and the steeper it is, the more gravity you have to work against until you're straight up and down, then you have to work against all of gravity, right? Why am I telling you that? Well, because that's what friction is. I have a special guest here today, SpongeBob. I always forget the starfish name. Sea star. Patrick, thank you. Patrick Sea Star. Yes, Thomas.
So if you have the ramp and it's like at an angle like this and you're pushing up,
Yeah.
if there's no friction on the ramp, what would change?
Well, so let's say I was pushing with 100 newtons, but the component of gravity I'm pushing against is only 80. That means I'm pushing against 20 newtons of friction, right? So I would still, even if there was zero friction here, I would still have to push against the component of gravity that is downhill.
If the ramp went on, would it go higher up if there was no friction?
The force would remain the same all the way, unless gravity changes.
So the gravity's the same and the force applied is the same, and then with or without friction, we travel the same distance.
I think so, yeah. If your force applied is equal to the force of gravity against you, then you'll travel at that constant velocity as long as you apply the force. Strange but true. But what if you throw it up there? Will it go up the ramp and stop? If there's no friction?
No, come back down.
Then it will go up and slide back down, right? Good sound.
Is it possible to make a frictionless surface?
Not that we have, well, no one's been able to do it yet. The closest we get is magnetic levitation. So
Oh, like the tunnels we were talking about.
Well, that's a great question, Sam. Why do we care about things like why would we want to have no friction?
Irritating.
So much more efficient.
Is the elevator? Because it's irritating.
You reach a higher speed.
Everything would be more efficient.
Everything we live in this world of friction, right? So everything you throw something, it's gonna hit the ground and stop. You try to slide something, it's gonna friction will stop it. But if you could have no friction, like let's say your commute. This is Elon Musk's thing. His commute from San Francisco to LA, let's say. Well, actually, he lives anyway. It doesn't matter. He has this commute in California, and he was stuck in traffic a couple times, and he was like, said something at SpaceX, and they were like, "Well, we should just build a tunnel." And he was like, "Yeah." And most people would just say that, but then he actually started building it. And the reason that they're building a tunnel is so they can pull the air out of it. Why would they want to do that?
As much
Then there's no air resistance and there's no friction, right? Very little friction. If you have a maglev rail and you push something, it won't slow down. It will keep going the velocity that you have imparted to it. So you could have, the idea is you're going to drive to this elevator, and your car will go down the elevator into the tunnel, and it'll ride on this skid plate that's magnetically levitated, and the thing will accelerate it up to 400 or 500 kilometers an hour, something like that. And after it gets to that speed, you don't need to input any energy into it. It will just travel that velocity. How do you stop it?
Yeah.
Apply force in the other direction.
But then
Yeah.
she's
So you're going to accelerate this is a little bit above your pay grade, but you would accelerate it with an electromagnetic field. And so it's kind of like, you know how positives, negatives attract?
Yes.
It's like that. You're going to attract it.
Negative.
And you're going to push this thing along, get it to this high velocity and let it go. And then at the end, when you stop it, the cool thing is, you stop it with a magnetic field. So at the beginning, you put in electricity, you make a magnetic field, you accelerate the object. What's cool is that at the end, you use a magnetic field to stop the car, and you get electricity out of it. So it's gonna take, you're gonna get a lot of the energy that you put in at the beginning, you're gonna get out at the end. And so you just keep recycling it. It would be a very low energy way to move people around. Anyway, sorry, I told you guys, don't let me go aside. SpongeBob is in his hamburger car. And they're sliding along. And it looks smooth, but as you found with the table, there's these little irregularities in the table, these peaks and valleys, right? It might look smooth and feel smooth, but when you get down to the microscopic level,
It is not.
it's not. You're gonna find that there's all these jagged edges. Even something that's really smooth like glass, if you look at it under a microscope, it's actually has all kinds of ups and downs and surface irregularities. That's what causes friction. If you think about these surfaces, they're like the ramp I just had. They're really small, but when you push this surface along, it has to lift itself up and over all the little bumps every time you move it. And so that's what friction is. You're going, and every time you have to lift a little bit against gravity. You go up, and you fall down, and you go up, and you fall down, and you up, and you fall down. And that's the force against you. It's really a component of gravity that's pushing you down all those little teeny little ramps. Bardia?
So this like relates it to both the material that is like sliding and both the material that is the ground.
Exactly. So the amount of friction, we're going to talk about this. I've had you calculating force of friction, but only when you know the other forces, right?
Yes.
So if you know the net force, you can subtract the other forces on the object, and you can get friction that way. But today I'm going to teach you a different way to calculate friction when you don't know any of the other forces, and you need to kind of build it from scratch. Here's the equation. Sean, what's your question?
If like a surface is like completely smooth, there's like no friction.
We've never made a frictionless surface.
Yeah, but let's say if there is a smooth surface,
If it's smooth surface, it has less friction, yeah.
but it's still not zero.
We've never made a surface with zero friction, no. The best we can do is lift something off the surface. Okay, here's the formula. Do you see it in the room?
Yeah.
Up here, right?
Whoa.
There it is. Fn is the normal force. You guys know about normal force, right? Gravity's pushing you down, normal force up. As long as the surface is flat, the normal force is straight up. This right here, it's not an M,
It's a mu.
it's not a U,
It's a mu.
it's a mu. So everybody say mu.
Mu.
This is a Greek letter. And this is the symbol that we use for the coefficient of friction. So Barty was saying the friction is related to the surface, and that's true. So if you had like sandpaper, for example, anybody ever use sandpaper? Oh, you know, when you're right? It's got a gritty surface. That would have a really high coefficient of friction.
Was that related to
Could
the
be
number?
7, 8, 9, or something like that.
Was that related to the grit? Like if you have 200
Definitely.
as opposed to 80?
Absolutely. If you had an 80 grit, that's a really high rough grit. That would have a higher coefficient of friction than like a 1200 grit sandpaper that you would use to sand a car smooth. It would be like much less. And something like glass, you know, if you had, what's really slippery?
Ice.
Ice. Like a hockey puck on ice would have a pretty low coefficient, somewhere like 0.1 or 0.2 or something like that.
Oh, wait, what's perpendicular mean?
Like a T.
This is perpendicular. So if my surface is flat,
It makes 90 degrees.
then my normal force is straight up. Yeah?
Okay.
But if my surface is tilted, my normal force is perpendicular to that surface. That's why it's called normal. In Latin, normal means perpendicular. I think it's Latin. Alexander.
What is the maximum amount of coefficient of friction? Like for
Infinite.
infinite?
It can be, and we'll deal
So
with
does
that.
that mean you always have to give us mu? Or is it like a certain number?
No, you might be able to solve for mu. I'm glad you said that.
But there's no units. So then what units do we put for mu?
There's no units.
He's just so cute. I just thought I would put him in there. Has nothing to do with any of us. Okay, I want you to know before we start and do some examples, there are actually two different situations. Get something on your desk, a calculator or something, or a phone, and just put it on the table. Just with a fingertip, push it, but pay attention to what happens right after it starts moving. Do you think it takes more force to start it moving or to keep it moving? To start it moving is always more. I'll tell you why, because remember we talked about those peaks and valleys?
You can feel it.
When something stops, those jagged edges, they kind of, I don't know how to show it. They like fit together. All those bumps slot down into the valleys and they're sitting there. And so to get it to move, you have to lift it up out of there. Once it's moving, you're kind of skipping along the tops of those peaks. Yeah. I used to use this example, but I don't know if you guys will know it. Do you guys know about cattle guards?
Yeah.
Yeah? Thomas, what's a cattle guard?
It's like, it stops, there's like a bunch of railings or metal bars, and there's gaps between them so that like cows and horses and any kind of farm animals can't cross gates or like leave a farm.
That's a pretty good example, a pretty good explanation. Let's say you have a farmer's field, okay, and here's the fence, and here's the fence, and you got cows over here. I can do a really good cow noise, can I show it?
Do it.
Ready? That's pretty good, right? Whenever I go to a field, I always do that, and the cows will. Doesn't sound. What's he trying to do? where I grew up, there's lots of gravel roads and there's lots of farmers' fields and stuff. And there used to be gates, and every time you drove, you'd have to stop at the gate and get out of the truck and open the gate. And drive.
That's so
And
irritating.
It was so irritating. And so they made these things in the road. They put these big, wide pipes
Oh.
in the road. They dug kind of a ditch, and they put these pipes across the ditch. And then the cows can't get across there because their hooves, they all get like jittery and they won't walk across it. But you can drive over it. But the pipes are quite big, and when you drive over them, if you drive slowly, you kind of go cocoon, 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 right? And the first time I was driving out on one of these gravel roads, I was like 12 years old. And my dad was like, I drove up to this thing and I didn't know what to do, so I slowed right down. I was like, cocoon, 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 you know, and my dad said, when you come up to a cattle guard like that, and I was like, yeah, I know, you gotta slow down. He's like, no, speed up. I'm like, okay. So the next one, I'm like, all right, and we went over it, and it was just like, didn't even feel it. Why?
Because it didn't have enough time to
You
like
just,
sink
like-
through each one. It just went
Exactly. Yeah, instead of going boom, boom, it went,
No, you
straight.
skipped over.
yeah, skipped over, kind of like skipping a rock over the waves, you know, just
Are you good at that?
pretty good. We'll have to go to the ocean one day and see. When you do static friction, everything is down in the valleys, and you have to push it up and it takes more force. Kinetic friction is when the object's already moving, and so you're skipping across the top of all those little microscopic valleys. Does that make sense, Hannah?
Yes.
Why is it mu s is greater? Oh, because it's.
Yeah, so static friction is always bigger than kinetic friction. Okay. That's just a kind of a little detail.
Why is it
Why
like
is
static?
Pardon?
Why is the static bigger than kinetic?
Well, if you think about it, you can figure out why.
I think
Because think about this. Let's just say that the static was less than kinetic.
It's not gonna start.
Let's say kinetic was 100 newtons and static was 10 newtons. Okay?
static is like 10 newtons.
Yeah. Let's say to start this thing moving, I had to only push 1 newton. But to keep it going, I have to push 2 newtons. Guess what happens? If I push with 1 newton and it starts moving,
It's gonna stop.
It's never gonna
then it's moving. Right? As soon as it starts moving, it's moving. So if I push with 1 newton and that starts it moving, well then my kinetic friction is already 1.
But why can't it just be the same?
Oh, so now we just keep going.
So it's like
It's-
the IDF.
It's not the same because things settle down. That's why.
Wait, so does that mean that if
So,
there's no
but if this is
acceleration-
2 and it takes me 2 newtons to start it moving, and then the force comes down, that's fine. There's no problem with that.
I don't understand.
Yeah, it's kind of a weird thing, but
Why?
Matthias.
So like the static friction is always going to be, or sorry, the kinetic friction has to be at least as much as the static friction, and then it can go down. It's got to be
Yeah.
the same as the static, and then it goes up or down.
that's right.
But it can't be
The kinetic has to be less than static. Otherwise, nothing would ever move. Sean.
What if it's like same?
They can be very close, but generally the static is more than kinetic.
Doesn't it have to be more because you just have to?
And it does, this stuff is all dependent, friction's kind of weird. It does depend on the thing as well. Have you ever put silicone on glass?
Yeah.
Have you ever done that? Sometimes it's like super hard to move. Like if you get something rubbery on a sheet of glass,
Yeah.
it's like literally that rubbery stuff gets stuck in the microscopic doodads, and it's really hard to make it move.
How does that work? Like how does?
It's almost like an elastic band. It gets hooked on a hook. You're like pulling it and you're stretching it. And then once it gets free, it's like
Does our skin have these ridges as well?
oh yeah. Your skin is crazy. And then it has all the sensors in it. We won't get into that. Izzy.
Doesn't that mean that like it needs like an acceleration to go? Or no?
It has to accelerate, yeah. Is my video still going?
Yeah.
Okay. We should carry on here. Let's do a couple examples. And hopefully that will help
Be
explain
it for the
things.
homework for the weekend. So go.
Right.
Really?
Maybe. Probably not though.
No, please.
Okay, so try this and see if you can do this. This is the basic stuff. We should start there. The basics. Sometimes when you do a problem, it helps to understand things a little bit more.
Drop it down.
Okay?
I don't know why I really want to understand.
Yeah, that's good. That's good stuff.
Well, where does math go into this?
Good question. Good question. I want to show you something. I drew. This is what I wrote out for my other class. Let me turn my phone so that.
Mu times.
Yeah, please do.
Oh yeah, what am I solving for?
That I assume.
How do we know what mu is?
And like identify which one is which and then what one you're missing.
Yeah,
it literally states what you have, it doesn't ask for it. Yeah, no, like.
Here's your formula. F equals mu Fn. Will you ever have to memorize this?
Yes.
No.
Where?
It's right there. I'm not going to cover it up. If the surface is level, then the normal force is equal to
Down.
gravity, right? Yeah, now you're just going like this. Yeah, that's right. So gravity is mg, yes?
Yeah.
So all you have to do to find friction, if you know the coefficient of friction, which sometimes I will tell you, and this is just based on the type of surface you have, then all you have to do is times by the mass, and then times by 9.8. That's your friction.
That's your net force.
So you would just say,
No, net force. Net force.
Are we doing mass times gravity or not?
yeah. So in this case, because we're pushing it along a flat surface, we're just going to do mu mg. So we have 0.65 is our mu, times 3.75 is our kilograms, and we times by 9.8, and you're going to get like 26 or something like that.
What is that 45?
Sean, sorry?
What is that 45?
Yeah, we're pushing the block with 45 newtons. Do we care about that?
No.
Nope, we don't need that to find friction. Oh, I didn't put the question up here. Sorry. You guys are like, okay, what's the question? That's the question, sorry.
You ever wondered what you guys use to buy a girlfriend? If you were a princess or frick or dad?
What?
I don't know what she was saying. Alexander.
You would use 45 minus the force of friction to get net force, right?
Yes, which we will. Which we will. So what's the answer for the force of friction?
24.37.
23.9? Oh, my thing's still slow here. Yeah, so I think if you calculate this out, the force of friction, mu times m times g. What is it? What was it? 23.9?
Yeah.
23.9 newtons. So let's draw a little free body diagram of this thing. The force of friction is going opposite to motion, right? So this thing is going that way. And we're pushing it with 45 newtons, right?
Sorry, Mr. E.
Yeah.
The camera's pointing the wrong direction.
Oh, thank you very much. That's better. So to find this, we did mu Fn. Fn is the mass times g, 9.8. And then we multiply by the mu, and we get this force. That's my friction force. Is that going to change if I push with more force or less force?
No.
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 Friction is dependent on the surface. So if I push this thing forward more or less, friction is not going to change. Friction is based on the coefficient of friction and the normal force. Okay. We're pushing with 45 newtons. This is 45 newtons here. What's winning at this point? The applied force is winning, right? So what kind of motion are we having here? Are we accelerating?
Yeah.
Yes, no. Yeah, we are accelerating,
Yeah.
Makes sense.
Is there a net force?
Yes, we are accelerating.
You just told me the applied force is winning because it's bigger, right?
Yeah.
So we have to be accelerating. Our net force is forward, and we must be getting faster. Yeah? Okay, so the next question is find the acceleration. Let me erase my Calibre thing here.
I don't have any of the variables.
Don't you? What do you need to find acceleration, Izzy?
Net force?
Yes, good. Can you find the net force? We don't know the acceleration, so we can't use mass times acceleration. But what else is net force?
MA.
It's all the
MA, yeah, but we can't use that yet.
Is it 5.6?
Sebastian?
Why we can use it?
Sum of all forces.
Very good.
5.7.
Very good, Matthias, as well. The net force is the sum of all forces. Now, can I just do 45 plus 23.9? One of these has to be negative, right? Because
Can we
they're
do
opposite.
friction, please? Friction, please.
Minus 0.3.
So let's make this negative. And then when we add them together, we'll get the net force.
That's loud.
I'm looking for a better marker because my black marker's running out. Let me see if I can. Athena, what's your question? Yeah, it's exactly the same. Look at this fancy marker. So net force is the sum of all forces. So we can say 45 plus negative 23.9, and that's going to be what, 21.1 or so?
Yeah.
Yeah.
Exactly.
So that's my net force. Now, net force is also MA. So if I'm going to solve for acceleration, how would I do that? Nairi, net force divided by mass should give me my acceleration, right? So if we do 21.1 divided by 5.63, 5.6 meters per second squared. That's my acceleration. How many people got that? Good, good, very good, very good.
I don't know who could write that.
So just to reiterate, and for the video people, to find the force of friction, we used friction equals mu Fn, which if it's a flat surface, is mu mg. So I told you the mu in this case, I won't always, but this time I did. So you take your mu times by the mass times by 9.8, that gives you the friction.
Yes, I do.
And then your applied force plus your negative friction will give you the net force. And then we just divided that net force by the mass to find our acceleration. Okay, ready for number 2? No.
Is there actually more?
Go. 0.2 kilogram puck. Hockey puck.
What do you mean if it was the constant velocity? I thought you said it has to have acceleration.
Well, the last one did because the forces were unequal. This one's moving at constant velocity. Good. Very good, Matthias. Amanda?
What is mu? Like, how is it determined? Like that
Well, you're going to do that in a lab. What you do is you measure the force that it takes to move something at a constant velocity. And then you know that the friction is equal to the force applied. And you can divide that by mg, and that gives you the coefficient of friction. Yeah, it's just something you measure. And as long as the surfaces stay the same, that coefficient will stay the same as well. Okay, so this is from a different one.
Did you get this?
So you got a hockey puck. and it's sliding along at a constant velocity, and we want to find the coefficient of friction. What are the
F
two
net
most
zero.
important words here?
F net is 0.
Okay, good.
Constant velocity.
Constant velocity, which means A equals 0. And as Izzy says astutely, net force is 0 as well. So if net force is 0, what does that tell us about all our forces?
Friction is equal with the applied force.
Good.
Does that mean it's not moving?
You tell me.
Actually, in real life, you would stop.
No, it would not.
Why not?
That means it's friction.
Inertia?
Let's say I have this book. I'm pushing it at a constant velocity.
When it's zero.
What's the net force?
0.
0. Is it going to stop? It will only stop if I stop pushing.
If you stop pushing. What is a one-time push?
Then no.
Well, then it will stop because then the net force will not be 0 anymore.
It's not a constant.
Right? Once you stop pushing it, then you only have friction. That's why things slow down and
So
stop.
why won't friction move the object?
Because you have a constant applied force.
Friction is only resistive. It is a weird force because you can calculate the force of friction on this book right now, right?
Yes.
But the book's not moving. So friction is weird. It's one of those real world things that doesn't fit the math that we created to describe it.
How do we know if it's moving or not though?
Well, you have to look at it and measure it, see if it's moving.
Oh, like if you give us like a question, you didn't say like, oh, it's moving, but like, oh.
I wouldn't do that. I wouldn't do that. You'll have to
It's
know.
so gonna be a problem.
Do you
It's
promise?
so gonna be a problem.
Okay, so these two have to be
Is it
equal,
moving or not?
Yeah.
right? Constant velocity means no acceleration, net force is 0. These two have to be equal. And so if we're pushing at a force of positive 0.24 newtons, then what's my force of friction?
Negative.
Good, negative 0.24 newtons. Now the negative is just direction, right? So if we want to find the coefficient of friction, can we do that?
Yes.
How are we going to do it, Nari?
You have to divide, the friction, the force of friction by mg, and then you're gonna get, so it's,
Okay.
so it's 0.24
Oh, sorry.
divided by 1.96.
Wait, why couldn't we use the top formula? Or that would just give us
Which top formula?
the FF is equal to mu.
That is what we're going to use. We're using this, but we're going to divide the normal force down here. With me?
Yeah.
Okay. This is a flat surface, so what's the normal force?
Same as this.
How do we calculate normal? Same as gravity, right?
Last time gravity.
So m times g. So if we do the force of friction over mg, that will give us mu, right?
Yeah.
And we know our friction is 0.24. So we're going to say this is 0.24 divided by, what is our mass? 0.2? 0.2 kilos, and then divide again by 9.8. So it's going to be like 0.1 or something like that?
0.12.
So mu will equal 0.12. About no units for mu because we're taking newtons and dividing by newtons. So they cancel out and you just have a number. It's just a proportion.
Why didn't we use negative?
You can, but the coefficient is kind of directionless. It doesn't matter what direction you push it in, it's going to have that coefficient, so it kind of disappears. No. In this case, this just means that the force of friction is against your motion. Pardon?
How is mu calculated?
What did I say last time? When Amanda asked.
I don't remember.
That's okay. We'll do it in real life and then you'll see it. And it will make more sense. Mu is kind of a strange thing. It's, I'll give you an example of why it's weird.
Like, is it possible to calculate it mathematically or not?
Yeah. Not without experimentation. You have to actually do something. So, if you're just struggling to hang on to this, if you're like this friction and muse, I'm not sure I get this, then close your ears right now and don't listen to this. If you're interested in the deeper stuff and you're like, I need to know everything, otherwise I'm never going to understand this, then listen to this.
It might be a power.
I have a book, right?
Yeah.
Force of friction on this book is mu Fn, yeah?
Yes.
I hold it here on the board, right?
Yes.
This is weird now. Is there friction on the book?
Yes.
Yes. There has to be. How do you know?
Because of the normal force.
If there was no friction, what would the book do?
It will fall down.
Fall down. Would it matter how hard I pushed it?
No.
I'm pushing straight into the board.
Yes, it does.
But if you like just push slightly, you will still fall down.
Which direction is the normal force right now?
Straight to the board. Or no, like
No,
no, that
Straight
backwards, yeah.
out of the board, right?
Out of the board.
So if I push harder,
The normal
The
force
book-
will be bigger.
well, the normal force will be bigger, and the force of friction, mathematically, will get bigger. In which means if I push harder, the book should go up.
Wouldn't it just go the direction?
Well, because what's pulling straight down on the book? Gravity. What's holding it up?
You.
Friction, not me. I'm pushing straight into the board. So if I push harder, I've tried this lots of times. It never goes up.
Push really hard.
Wouldn't
It
just
never
go
moves
the
up because even though I'm pushing more and the normal force grows, friction will only resist the force that is present there. It has to have motion in order to be active. So you can calculate the math all you want, but the force is not going to be there unless there's some motion for it to resist. Or some force for it to resist, in which case, in that case, it's gravity that it's resisting, right? So it's one of those things where we make the math because it works most of the time, but the math doesn't
Apply to
encompass
every
the whole thing in reality. We did this, right?
Yes.
Okay, I'm gonna turn my video off. Hopefully that's good.
Oh, there's another problem. There's example 3. I was looking at the slides.
I blame Izzy for this. There is example 3.
Can we agree that physics is weird?
Oh yeah, physics is weird.
Yeah.
But great too.
Yes, I agree.
Kind of like me.
Everybody was
I
quiet.
know. Nobody said anything.
It's okay, we agree.
You know I'm weird at least.
Yes.
We're at 25 signatures, Mr. Espinel. You can't be that bad.
I agree. Thank you, Thomas. 1.1 kilogram textbook held against the vertical wall.
Did he?
And I'm pushing with 45 newtons. What is the coefficient of friction between the book and the wall? I have to actually tell you something else about this. I'm just holding it up. So if I exert any less force than this, the book will slide down. Okay. It would have to be that situation. I could push with more force than this, and then you have nothing to calculate.
How do you know it has to be 45?
This is a terrible example though, so I'm not going to give you this example. But let's just do it. Oh, it is strong.
How do you know it has to be 45 though?
How do you know what?
It has to be 45 to keep it up.
Only because I told you. I would have to tell you that. If I didn't tell you that, then it would be useless. So our normal force is 45, yeah? Yeah, but in this case, because you're pushing horizontally into a wall, the normal force has to be equal.
Wait, wouldn't it be negative
So-
45? Since
It's
you're
perpendicular
applying
to the
45.
wall, so
Yeah, but you're applying 45, the other way would be negative 45, no?
sure, but it doesn't matter.
One of them has to be negative, no?
Yeah, but negative is going to get mixed up here because we have out and in, and we also have up and down,
Right.
so they stop meaning anything. So you've got your book. Here's the wall, and here's the book. Gravity on the book is going to be what?
Last time.
10.38.
1.1 times 9.8, right?
10 something.
That's gravity, which would be
10.38 lift.
10.38?
No, I'm not sure.
Can we just do it as like 10.1?
10.78, sorry, 10.78.
No, I think it's less than that.
No, it's 10.7. I use
10.78?
Yes,
Oh, good.
10.78.
10.78. So that's our normal force down. Sorry, that's our gravity force down. So the friction has to be the same, right?
Yes.
Why does that have to be the same?
Because otherwise it would slide down or move up. It's got to be the same. So we have our normal force and we have our friction force, which has to be the same as gravity. So let's just say 10.8 newtons. And so if you want to find the coefficient of friction, are we able to do it now?
Yes.
Yeah, you just use your formula, right? Same process as this one. Force of friction over normal force. So we're going to say 10.8 over 45. This is kind of a weird example. So it's going to be like
0.23. 0.23.
0.23.
Yes.
0.24.
Okay.
4. Oh, that's
And this is
God, it's one.
mu is equal to 0.23. Okay, now I'm going to put the big. I'm getting a new phone for Christmas. Shh, don't tell my daughter.
Which one?